I'm going to be talking about quantum nuclear dynamics, and I've tried to, I realize the audience is pretty diverse in terms of background, and so I've tried to put all the information you'll need to kind of keep track of what I'm talking about, but please do feel free to jump in and ask me to go back and explain something that you haven't seen before. I watched several of the talks that have been really interesting to follow, and I noticed that there's a lot of electronic structure, and so I am possibly the only one who's going to be touching on nuclear motion here. So just very briefly to give you an idea of what motivates our work, these are the kinds of chemical applications my group is looking at. Roughly speaking, the typically photo-induced processes or occurred in some type of excited state, so electronic or vibrationally excited dynamics, sometimes photo-induced, sometimes thermally driven. And the kind of unifying theme here is that there are multiple electronic states typically involved in the dynamics, and there are also motions on multiple different time scales and length scales, necessitating sort of an understanding of both quantum mechanics and just classical mechanics as well. And so we recognize that in trying to achieve a realistic simulation of something like this rather complicated looking redox complex that's involved in a dye regeneration mechanism for a dye-sensitized solar cell, for instance, you really want to be able to capture the large-scale motions with classical mechanics while also acknowledging, of course, that there are important quantum effects, zero-point energy, coherence effects, and tunneling that you would want to take into account. And our goal is to try and do this in a rigorous framework. So we're not just slapping together quantum mechanical treatment of one part of the system with a classical treatment of the other, which typically gives rise to what are known in that area as boundary problems, where the classical portion fails to talk correctly to the quantum portion. And so we're really trying to build up this semi-classical framework that will allow us to access these large-scale system simulations. So I'll start really basic and introduce you to the terms I'm going to be using in this talk. So of course, the time evolution operator, we all know, has the form of this exponential with the Hamiltonian in it. And then what we call the propagator is really just a matrix element of this time evolution operator. And the idea is that this object describes the probability of starting in some state X and ending up in some other state X prime at time T under evolution of a Hamiltonian. And just to make it clear that our focus really is on the nuclear side of the problem, I'm defining my Hamiltonian as the kinetic energy of the nuclear degrees of freedom plus a potential energy, where the potential energy surface is, in an ideal world, of course, the solution to the electronic Schrodinger equation at every single nuclear geometry that you would access in your dynamic process. More often, it's some type of effectively parameterized potential for a realistic system, and that one hopes the parameterization was also done based on electronic structure calculations, or you could imagine a model potential that you're working with that describes condensed phase behavior, so fitting a spectral density or something like that. But really, our Hamiltonian we are, for now, assuming that the electronic problem is either solved or sufficiently solved that we can now address the dynamic problem. And the dynamic observables that I'll be talking about calculating are these correlation functions, which are really just the most dynamical observables in an experiment, like a spectrum or a diffusion constant or a reaction rate, correspond to these types of correlation functions. And the simplest form is a trace over operator A at time 0 and operator B at time t. And of course, in the Heisenberg framework, the time-evolved operator is then shows up with the propagator on either side of it. This term we refer to as the forward propagator, and then this term would be the backward propagator. Okay, so a common example of a correlation function of interest is what's called the reaction rate. And again, a lot of reaction rate theory is derived from classical statistical mechanics. But a reaction rate here you could think of as, for instance, a flux side correlation function. The flux operator would look at the velocity of moving towards product formation. I've shown a simple picture of a reaction potential energy here, but I have reactants, products, and some type of barrier corresponding to, let's loosely call it a transition state. And the idea is that you can look at the velocity of your trajectories that pass across this barrier and correlate that with how many of them then end up in the product state at time t. And the long time limit of that correlation function is a direct measure of the rate of a reaction. So that's just an example. To actually get into the methods that we use, I want to introduce the path integral representation, which most of you have probably seen before. This is just a simple cartoon explaining how this works. So we take a quantum propagator, so starting at some point state x0 and ending at some state xn, and you can write it as a sum over all possible paths in space. So this is our phase space representation of quantum mechanics. So you start in some initial condition, and you can imagine drawing all possible paths that connect this position to a final position in time t. And when you summed over all of those paths, where each path contributes a phase that is due to the action of that path. The action, of course, is a classical object. It's the time integral of the Lagrangian. That is going to give you the phase contribution of each path and then divided by each bar, which allows you to then construct the classical limit of this path integral property. So if you look closely at this idea of summing over the infinite numbers of paths, of course, that doesn't seem like a very computationally feasible thing, but there's an approximation you can make right away, which arises from just basic classical mechanics, which is that we know classical mechanics, Hamiltonian mechanics tells us that the classical paths are the paths that obey this stationary action principle, which is delta S equals 0. And so if you think about summing over all possible paths to go from one position to the other, you could argue that the classical path is going to be reinforced an infinite number of times because it's infinitesimally small variations to a classical path will have the same action as the underlying classical path. And so the classical path and its infinite variations are included in this sum, and those are going to have the same phase, whereas you could argue that a path that's far from classical would have a very different phase and experiences a lot more phase cancellation when you sum over all of these paths. And so that's one argument that allows the path integral to work well in the semi-classical picture, where you then make the approximation that rather than summing over the infinity of paths, I'm now going to sum over only the classical paths that get me from x0 to xn. And you'll notice there's more than one classical path because, of course, classical mechanics is only deterministic when you specify initial position and momentum. And so this more straight path would be maybe a low momentum path, and a faster moving particle might go through a slightly different and longer path to get to the same final position. And so the idea is you have numerous classical paths, and you can sum over just all of those, and also include a few paths in the neighborhood through a stationary phase approximation. So the mathematics of this is pretty straightforward. You take this expression with the action integral, and you Taylor expand around the classical action, and you truncate to second order. And this is a reasonable thing to do, again, because you know classical paths are the most significant contributors to that integrand. And this gives you what's called the semi-classical propagator. So in the form that I've provided it, it's actually what's called the Van Vleck-Goetz-Willer propagator. If you work in a coherent state representation, you can derive a Hermann-Kluck representation of the propagator. But independently of what representation you choose, the idea is basically the same thing. You go from a propagator that required a sum over a large number of paths to a propagator that now only sums over the possible classical pathways, and you introduce a prefactor from your stationary phase approximation that effectively accounts for paths that are each bar close in action to the classical path. And so you have this sort of tube of paths that you think about including in a semi-classical calculation. And so this is kind of the pictorial representation of that, where you now have a reduced number of paths, and then you have a prefactor term that accounts for this volume and phase space around your classical pathways. Okay, But I told you the quantity of interest for us for a dynamic observable is a correlation function, which now has two of these propagators. So the actual calculation we think about is going to have a forward propagation and a backward propagation with these two operators, which could be positions, flux side, depending on the observable that you're trying to calculate. These will vary. If it's a thermal process, operator A will frequently be what's called the Boltzmann operator. So you'll have a thermal distribution operator times a dynamic observable here. The structure of a correlation function looks very much the same, independent of what these operators are. And that is, you start at an initial state, you time evolve forward for some amount of time to a new time state at time t. Operator B will then act on that new state and displace it in some way to generate a different state, also again at time t, and then you'll time evolve backwards to a new state at time 0, and the matrix element of the initial and the final state appeared with operator A in your expression. Okay, so that's the structure of a correlation function calculation. And if I were to do this with exact quantum mechanics, I would have to sum over two independent sets of infinitely many paths. And the only connection between these paths is going to be through the operators of interest. So operator A and operator B will establish some constraints on how similar or how different these endpoints will need to be. Okay. So if I were to make the straightforward semi-classical approximation to the two propagators, I would then end up with that same cartoon I showed you, where I now only consider classical paths forward and backward, and I have a prefactor that accounts for the phase space volume in both cases. And again, I have this displacement due to operator B at time t. And the classical picture here, of course, would take this one step further. If you were to look at a purely classical mechanical correlation function, there is no forward and backward path because operator B, of course, is not an operator. It's a simple function in the classical world. And so you'd end up with a perfect coincidence of forward and backward paths. Your net action is 0. And so you would really just evaluate operator A at the position at time 0 and B at time t. That's classical mechanics. If you want to think about classical limit semi-classics, meaning we take the semi-classical expression and we make one additional approximation, which is now based on this idea that I don't treat my forward and backward paths as completely independent. I instead allow them, require that they be infinitely close to each other. And so effectively, I'm making this displacement limit 0. They don't have to exactly coincide because the difference between classical limit semi-classics and straight up classical mechanics is that you're still going to have these phase-space distributions at time 0 and time t that correspond to Wigner distributions or Husimi distributions or some type of phase-space structure of your operators. But your net action will still be 0 because the forward and backward paths will be close enough that you have no effective phase. And that gives you what we will broadly refer to as classical limit semi-classics. There's a lot of variations within that exist in the literature. Okay, quantum limit versions of semi-classics are really just the original semi-classical approximation. Has no explicit bounds on delta x or delta p. They are, of course, implicitly limited by the stationary phase approximation that you made for the original path integral and the structure of the operators. Okay, so this is where our idea of building this sort of mixed quantum classical framework comes from, is the recognition that you can make the semi-classical approximation and then you can make further approximations within that framework. And you could do this in a degree of freedom specific way. Okay, so how do you do that? A simple way to think about doing that would be to filter the phase contribution from these pairs of paths. So I've pointed out that the only difference between a classical and a quantum limit implementation is really the extent to which you allow these two paths to differ, because that difference is what contributes to the phase term in your integrand, and that's what makes it hard to evaluate. So the dynamical sign problem, as we call it in semi-classics, comes from having to integrate over this difference in action term that is, of course, an oscillatory integrand and can therefore become extremely hard to numerically converge for large high dimensional systems. And by high dimensional, I really mean beyond a handful of degrees of freedom. And so the question is, can we mitigate this problem for high dimensional systems by controlling that phase and trying to hit that sweet spot where we include the right amount of phase, but not a lot of unnecessary phase that would need to be numerically integrated over. So we start by just figuring out how to filter out contributions from trajectory pairs according to the size of this net displacement that I was showing you. And the way we're going to do this is to use what's called the modified Filonov filtration scheme. So this has been around for a long time. It was first introduced in the context of semiclassics in 1988, really, when a Filonov filtration scheme was proposed to reduce the oscillations in a semiclassical calculation. But I won't get into the details of it. If you're familiar with this area, the generalized forward-backward method is what arose from that first use of the filtration. And it was it was sort of a simplified version of what I'm going to show you, which allowed some amount of phase control over a double propagator scheme. But the way we're going to use it gives us a much nicer result, a much more numerically satisfactory result, I would say, where you start with an oscillatory integral and you end up smoothing the phase. And the choice of phase is a lot of what the problem comes down to in semiclassics. But let me walk you through just the Filonov filter. So you write your integral as a simple product of a g of z and an e to the I f of z. F is in general a real valued function. G can be complex. And this is where the choice of phase becomes important, because you don't have to filter all of the phase. You can filter some and you can choose what phase to filter. Once you made this choice of g of z, the structure for your integrand, the modified Filonov approximation just multiplies your integrand by this function f that I've shown here, which really is just a Gaussian in the first derivatives of your function, of your exponential function, and it gives you a determinant structure. This may not mean a whole lot until you recognize that if you were to take the c goes to infinity limit of this expression, what you arrive at is the stationary phase approximation to your original integrand, right? And so you're expanding around the stationary phase where f of df by dz equals 0 is the point that you're performing the stationary phase expansion around. And that makes this incredibly powerful, because you now have these two nice limits where, of course, if you set your filter strength c to 0, you get back your original integral, nothing changes. If you make it go to infinity, you get a stationary phase approximation. Okay, so how can we use this? We went ahead and used this to tune specifically only the phase due to the difference in action between these two paths. Right? So our filter specifically filters the delta x and the delta p, which are our phase-space displacements at time t. And so once you've done I'm not dragging you through any of the derivation, but once you've actually worked through the math, what you end up with is a fairly straightforward structure for your correlation function. So you have a phase-space integral over your trajectory endpoints. Rather than integrating over x0, p0, and xt prime, pt prime, which is the initial conditions for the backward trajectory, we choose to integrate over the displacement operator. So you can do a simple change of variables. So those are your integrals here. And your exponential with the phase remains untouched. That's the difference in action between the forward and the backward paths. Your prefactor, which I'm not actually explicitly showing you, is composed of derivatives of positions with respect to momenta at time t and time 0, and is going to depend on these parameters as well. And you have these operator matrix elements, which is the same thing that you had in the original semiclassical expression. I'm working with coherent states now to facilitate implementation. And you end up with this Filonov filter term, as we call it, which has these exponentials that are just Gaussians in the displacement. And so you can see right away that you end up with this really nice structure where if I set these Filonov parameter values to 0, then I get back my original integral. And that is just a standard semiclassical approximation, the full semiclassical approximation to the path integral, or what we'll call the quantum limit. If you set these two filters to infinity, what you're doing is selecting for extremely small displacements, delta x and delta p, and that gives you the classical limit of semiclassics, right? And what makes this powerful is that these are now matrices, that they're diagonal matrices that are the dimensions of the number of degrees of freedom in your system. So for an n-dimensional system, you'll have n of these parameters, and you can choose them to be all zero and all infinity to explore the two extremes, or you can start making choices that are somewhere between the zero and infinity. Okay, so this is just saying what I already walked you through, which is that you can show analytically that in the two limits, you reproduce either a quantum limit semiclassical or a classical limit pre-existing semiclassical theory. Your prefactor also depends on these. And so the prefactor is complicated if you're looking at a coherent state semiclassical calculation. It turns to, in the limit of these filter strength being infinitely large, it goes to 1, which is exactly what you expect in the classical limit. And these are, as I said, n by n diagonal matrices. And so you can now choose how quantum a mode is without affecting the underlying dynamics of the system, because the dynamics are still going to be driven by a full calculation of the classical dynamics for your system, time evolving from time 0 to time t and all your degrees of freedom. And the only thing that this filter does is to choose which paths to include. So if you decide a particular mode is not very quantum, all that means is that any contributions of that mode that where there are large displacements at time t will be ignored in favor of paths where there's a small displacement at time t. But of course, if you displace one mode and it's strongly coupled to another mode, there is a second order displacement that you'll see that is fully accounted for. Okay, so here's a numerical example of this. We took a simple one-dimensional n-harmonic oscillator. We started our system in an initial coherent state, and we made operator be just the position. And if you look at the quantum mechanical position correlation function for this system, you see that there's what's called a quantum recurrence, because of course you can't lose 0-point energy in a quantum calculation. And so you see the amplitude of the oscillations damp and then grow again. And if you run this out for a long time, you'll see the same sort of structure emerge. So if you run a double Herman-Kluck, which is the quantum limit semiclassics that pre-existing, that was what our framework was based on, you get these dashed lines that basically capture the quantum recurrence pretty well. If you run an MQC calculation, so this mixed quantum classical method we're introducing, with a Filanow value of 0.7, you end up with the pink curves, which capture the recurrence, but you start to see a little bit of damping. And as you turn the parameter up, when you hit about 500, that's your C goes to infinity limit. You see that you reproduce the classical result almost exactly. And just for a sense of how expensive these things are, I've showed you what our convergence parameters look like. So the Herman-Kluck takes about 3 million trajectories to converge just for the simple one-dimensional system. The exact quantum calculation, which we do using a DVR grid, is actually much, much cheaper and faster. The MQC calculation, even with a small value, takes only about 10 to the 4 trajectories, and then it just gets cheaper as you get less and less accurate, of course. And what's interesting to us, I would say, is that this small value limit, the marked improvement in convergence properties with a small value of the filter is what we were most excited about at the time, because it makes you realize that you can get a lot of quantum behavior without going to quite as much the expense of a C equals 0 result. And that, of course, is going to vary from system to system what these actual numbers are. Okay, so how does it work? There was an original paper written a while ago, soon after Filanow filtration made its appearance in semiclassics, talking about how when you propagate a wave function, so you have just the single propagator, the Filanow filtration scheme is effectively useless. What the paper very nicely showed, this is a Batista and Brumer paper, was that because you're filtering the phase of the quantum propagation, when you turn the filter strength to a large value, you effectively are missing most of the important quantum effect. And in the in the context of a correlation function, the way that we use the filter is very different, but we wanted to look at what the phase we were filtering was and make sure that it was actually what we thought it was. And so here's an analysis of that same 1D enharmonic oscillator that I showed you. What we're doing with this oscillator here is, if you recall, the calculation involves an operator B that's a position operator. So when operator B acts in a coherent state, it does not change the position, it only changes the momentum of that state. Right? And so the only thing that you have a jump in at time t in the between the forward and the backward paths in this particular calculation is in the momentum. And so we look at the Filonov parameter associated with just the momentum jump variable. And if you look at that, this is for a single trajectory. So I start with an initial phase space point and I run it out for a time t. And I look at, as a function of this delta p variable at time t, I plot the phase of the integrand and the amplitude. And you can see that the phase looks remarkably the same no matter what actual Filonov parameter value I use. Right? So remember, the Filonov parameter only shows up in the prefactor and in those exponential Gaussians, which of course don't contribute to the phase of the integrand. And so the phase really doesn't change very much if you change the value of your filter strength. But the amplitude, of course, changes dramatically because you're effectively multiplying it by a Gaussian width. And so you can see that as you go from 0 to infinity, which is the purple to the red, your amplitude moves towards being just a delta function in this delta p term. So a Gaussian in the limit of an infinitely narrow width, of course, collapses to a delta function. And so what you're doing is the phase is unchanged. But if you then think about your integrand, which is the product of the phase and the amplitude, you can see that this classical limit, when c is infinity, is only going to multiply phase that's relatively stationary. And you're eliminating all these regions of extremely noisy phase. So let's see what actually happens when you use a large number of trajectories, as we would do, to do an ensemble average calculation for the correlation function. So here's the phase again, and this is for a large number of trajectories. So it's the average phase that you get from a large number of trajectories, and we increase that from 1,000 to 10 to the 4 to 10 to the 6, which is how much we needed to converge the semiclassical calculation. The phase is basically the same no matter how many trajectories you run. Your average phase always looks like this. The amplitude does something really interesting. So if you just look at the gray and the red and the blue lines, this is the amplitude of the integrand for a full semiclassical Hermann-Klick calculation. And you see that it's incredibly noisy with 1,000 trajectories in these regions that we're calling the noise regions. This is roughly my region of stationary phase where I can get meaningful information. And anything that amplifies these regions leaves me with a dynamic sign problem. And you can see that as I increase the number of trajectories, what I'm doing is effectively damping the amplitude in these regions of noisy phase and starting to make the amplitude near zero. This is without any of the filtration that we've introduced. So now if you introduce the filters that we use, these Gaussian functions of differing widths, you can see what happens at a C of 0.7, which is where we got those really nice results that looked sort of like quantum recurrences. Effectively, you can see that the Gaussian envelope that multiplies my integrand has this very nice structure that mimics the blue line, which is our goal, right? The blue line is quantum limit semiclassics. And the green line effectively makes sure that the amplitude goes to zero in all regions, exactly zero in all regions outside of that. And so you have this significantly improved convergence because even these small as these amplitudes look, you multiply them by a phase and you try and sum over the integral numerically, you're giving yourself a sign problem. And so by actually explicitly cutting out the amplitude in this region and setting it to exactly zero, you're saving yourself a lot of trouble. You can see that as you make the filter even weaker, so you start moving towards quantum limit, you get back some of that noise because now my Gaussian that I'm multiplying by is much broader. But what this really nicely shows is that you can, with a correct choice of this Filonov parameter, really overcome the sign problem by simply eliminating regions of noisy phase that are not physically useful. The obvious question that this raises then is, well, how do you know what that magical number is? You know that if you went if you were at a c equals 0, you're doing exactly the right physics, but you're numerically never going to converge that calculation. At infinity, it's the wrong physics, but it's extremely easy to do the calculation. So somewhere in the middle is the sweet spot. And the question becomes, how do you find that for each system, which is a non-trivial question and one that we don't have a very good answer to right now. I'm going to skip the implementation details and jump to what happens now if we do a mixed limit calculation. So I have a two-dimensional system here. So it's that same anharmonic oscillator that I couple to a heavy harmonic mode. And we look at the position correlation function of the lighter anharmonic oscillator. And the question we wanted to ask here was, what happens when you have a heavy mode coupled to a light mode, and you want to look at the dynamics of the lighter or the more quantum degree of freedom? Can we make a numerical saving by allowing 1 degree of freedom to be in the classical limit? If you remember, that was one of the motivations for this entire scheme. And so we look at, there's a lot of pictures, a lot of colors in here. I'll draw your attention to the tail end of this graph. I should have provided you with an inset here. You can see the oscillatory structure really dampens when you go to the classical limit, which is the dark blue line, as opposed to the black line, which is your exact quantum limit. And so if you look at the pink line, corresponds to a quantum limit calculation where we have our filter set to a pretty weak value, right? So Cx equals Cy equals 0.2. So we're filtering both degrees of freedom to the same extent. We're working with both of them in the quantum limit, and you reproduce these long-term oscillations pretty well. If you then look at a case, the cyan line, the light blue line, is where I treat X in the quantum limit, but my Y degree of freedom is set to a filter of 100, which is effectively now a classical limit calculation. And you can see that I lose no structure at all. So this really argues for the power of kind of this mixed quantum classical limit, where you can genuinely quantize 1 degree of freedom and put the other in the classical limit and still get the quantum behavior of your overall system correct. We did also look at the Y correlation function. Because it's more classical, the results simply look less interesting, but it bears out the same statement. Okay. As I mentioned, some of what we're interested in is what's called non-adiabatic dynamics. I don't have a lot of time to go through the details of this, but I did want to have a slide that pointed out that in the semi-classical literature, there are ways to treat a Hamiltonian where you have a nuclear degree of freedom coupled to multiple electronic states. When I say non-adiabatic dynamics, what this refers to is frequently in photochemistry, you have a situation where there's not just one sort of pathway for your nuclear wave function to take. There are multiple electronic states that couple to the nuclear transitions. And so your Hamiltonian is written in a somewhat more complicated form where you have the baseline nuclear kinetic and potential terms, but then you have this coupled term that involves the potential from multiple electronic states and the coupling between them. And there is a way to transform from this discrete electronic state representation using these bosonic mapping variables to a Cartesian form for the Hamiltonian. The reason I mentioned this is because we wanted to look at how this mixed quantum classical behavior applied to a non-adiabatic problem, right? So our interest here is not in walking you through the Hamiltonian, but simply that I now have this Hamiltonian that has been shown to effectively capture multi-state dynamics. So can we look at that with this mixed quantum classical approach? So here's a model 2-level system again. So this is state 1 in gray, state 2 is in black, and the coupling between them is in red. And the idea is that you start an initial nuclear wave packet on the upper state, so that would correspond to a photoexcited state, let's say. And as your wave packet evolves in time, it goes through this avoided crossing and now has 2 possible transmission channels, an upper channel and a lower channel. And the probability of transmission on these 2 channels is going to be driven largely by the initial momentum of your nuclear wave packet. So you can imagine if you come in at a very high energy, you would not necessarily favor one over the other, whereas if you come in at a lower energy, close to the energy of state 1, you would heavily favor transmission on the lower channel, which would correspond to a higher momentum. And so the question is, can we look at this with our tuning approach? And so if you look at a correlation function where A again is just the initial state of your wave packet, and B histograms the final momentum. So a high momentum would correspond to transmission on a low potential channel, and a low momentum would correspond to transmission on the upper channel here. Okay, so this is a calculation I actually had done as a graduate student working with Bill Miller, where we looked at this probability of transmission using two different semi-classical methods, one a quantum limit method and the other a classical method. And what you see is that the classical limit linearized method basically just does not capture this idea of branching at all. What ends up happening is that you see transmission on some average potential surface. It's an average of these two. And so you end up seeing transmission at an unphysical momentum value, and you see a single peak. If you look at the quantum limit, you see the sort of double transition structure you expect, but you can see that the exact quantum result is in black and the semi-classical result is in red, and it's considerably noisier. But you do capture this sort of branching ratio idea with the semi-classical calculation. There's some details about the integrator that we had to work out to develop a symplectic integration scheme for this Hamiltonian, but here is the punchline. So you can look at the MQC correlation function results for different values of the parameter. And here I put my filter strength to be the same for all degrees of freedom. So the electronic and nuclear variables are all being filtered to the same extent. And so when I'm very quantum, so a C of 0.1, I basically reproduce the exact quantum result pretty well. And then, of course, as I go more classical, I start to see this single peak structure emerge rather than transmission on the two branches here. Okay, and this was an interesting thing to us because what we're probing, remember, operator B is a nuclear operator. And so our question was, even though in a non-adiabatic system, the nuclear motion is very, very strongly coupled to the electronic motion, is it possible to do a sort of mixed quantization where we treat them in different, quantize them to different extents? So the plot on the left is where we quantize the nuclei by fixing the tuning to be a very small, the filter strength to be very minimal. And then we look at different values of the filter for the electronic degrees of freedom. And interestingly, you see that as you push the electronic degree of freedom to be more and more classical, you get a somewhat unphysical distribution, but you continue to see transmission on two channels. So you continue to get this idea of branching right as long as you quantize the nuclei. If you quantize the electronic states and treat the nuclei classically, which is maybe more intuitive, for this particular observable, you actually do almost worse because I quantize my electronic state, but my nuclear filter is now turned on to a strong value, meaning my nuclei are classical, and I end up seeing this average transmission. Right, so this also ties into the other interesting thing about this MQC framework, which is that if you have multiple degrees of freedom, you can choose to quantize one more than the other. The choice of which one you want to treat quantum mechanically should really be motivated not by your absolute intuition as to who's quantum mechanical and who's classical, but actually the structure of the observable that you're interested in. If you're probing a nuclear degree of freedom, it becomes essential that you allow the nuclei to move in the quantum limit and not the electronic degree. The electronic degrees of freedom here are important, but not as important. And that's one interesting observation. The other thing to note, of course, is when your degrees of freedom are very strongly coupled, you start to lose fidelity when you mix the quantization extents. Right? And this also makes sense because, of course, strong coupling means the displacement in one degree of freedom will automatically displace the other degree of freedom to a large extent. So attempting to wash that out is going to give you unphysical results. So this tells you something about the importance of physically partitioning the system appropriately to try and identify those regions of weak coupling rather than going with the sort of a mass-based quantization perspective. Okay. So the MQC method works really well. We've since used it for numerous other applications, but there's bottlenecks in this calculation, primarily arising from the fact, as I mentioned, you have to find these optimal values. And we're building an error correction framework that helps us get there. But there's some amount of, I do think there's an interesting conversation to be had about what is the best way to identify what these parameter values should be, how to choose a filter strength. The prefactor is another big problem. So I've carefully avoided showing you equations for the prefactor because they're extremely large and clunky. Effectively, as I mentioned, they're Jacobians of the phase space variables in time. The challenge arises from having to, the form of the prefactor is, it's the square root of the determinant of a complex n by n dimensional matrix. And so you need the Hessian to time evolve the prefactor, which is a second derivative of the potential, which is something that's hard to come by unless you have an analytic potential. And the other thing is, if you're taking the square root of a complex number, as you know, you have to numerically ensure that you're taking the continuous square root of this complex number. And so that means that you actually have to implement strategies to systematically check that you're staying on the same Riemann surface. That's fairly trivial, but it does impose a time step requirement in addition to the MD time step that's not usually pleasant for a large system. So we looked into deriving an analytic mixed limit, meaning, of course, you could argue that rather than messing around with small c's and big C's, let's just take this picture all the way. Let's say I have f degrees of freedom that are quantum and the remaining are going to be treated classically. Let's set my filter to 0 for those f degrees of freedom and set it to infinity for the rest. And it turns out you can arrive at an analytic expression for this. So we derived that, and we actually showed that your prefactor then can be reduced significantly to what looks like a full semi-classical prefactor in the f degrees of freedom times a term that accounts for the coupling between the quantum and the classical modes, but there is no prefactor associated with the modes that are in the fully classical limit. They only show up in this coupling term. And so when you do that, you could then do what we call a separable prefactor approximation, which is basically throw out the quantum classical coupling. That is an ad hoc approximation, obviously, but that also would then reduce the dimensionality of your prefactor considerably. And the question is, where does this work? And the sort of straightforward answer is it works when you have weak coupling between your quantum and classical subsystems, right? So here's my 1D harmonic oscillator again. This particular model that we looked at, it's my 1D n-harmonic oscillator coupled to my heavy harmonic mode. AMQC is the analytic limit form of our solution, and the blue curve is the separable prefactor solution. And you can see that in this particular model, the separable prefactor does just as well as the analytic. But if you go further and you look at a truly high dimensional system, so this is a standard proton transfer in the condensed phase model system. So it's just a double well potential for the proton coupled to a bunch of harmonic oscillators that describe the bath spectral density. You can look at the transmission coefficient, which is the quantum rate over the classical rate. And the exact result is from a Nancy McCree paper. And you compare that to the analytic MQC IVR result, you can see that our mixed limit does really well here. This is the full limit where we just treat the proton as quantum mechanical and we treat all the other environment modes as classical. But you also find that if we impose the separable prefactor, it really only works in this regime. This picture, the x-axis here is the strength of coupling. It's the friction term, or effectively the strength of coupling between the proton coordinate and the path of the environment. And you can see that as you increase the strength of coupling, the separable prefactor approximation fails completely. So in this very weak coupling regime, you do well, and otherwise you don't. So this is not an approximation that we recommend. So right before I wrap up, I'll just point out one really exciting new direction where we've been going with this, which is that we're pretty happy with this mixed quantum classical implementation, and there's a lot of room to now bring in other approximations that people in the semi-classical world have developed over time, that none of which we currently use. But another interesting question to ask is that the exact path integral expression for this does not have this prefactor problem. There is no prefactor. The prefactor arises from the original semi-classical approximation. And when you go to the classical limit semi-classical methods, they also do not have this prefactor. And so we asked the question of, can we identify how to filter the phase of an exact full path integral expression for the correlation function to obtain a classical limit semiclassical method? And it turns out the answer is yes. It's a little more complicated than one would like, but effectively, I'll ask you to ignore all of this. This is simply a different way of writing the integral over all paths. We work in mean and difference variables rather than forward and backward paths. So you have an average mean path and a difference variable path. But that doesn't change too much. The filter, however, is interesting. So you end up with these exponentials. This should be an exponential as well. You end up with these exponential Gaussians, which filter the difference variable between the two paths. And this fj, which is defined as this derivative term. And some of this doesn't make a lot of sense until you look at the limits. So in the limit now of all of our fill in our parameters going to 0, you get back your exact path integral. That's great. In the limit of c going to infinity, you actually get a pre-existing semiclassical limit method called the linearized semiclassical method, which is basically an integral over Wigner distributions at time 0 and time t of the two operators. And the way that this comes about is because you recognize that when you work in these mean and difference variables, so instead of working in forward and backward paths, I have an average path and a difference between the two paths variable. When I take the limit of c going to infinity, what I'm actually doing is setting z to 0 at every step along in time, meaning the forward and backward paths exactly coincide, which is our understanding of classical limit methods. But also it sets this fj parameter to 0. And fj being 0 actually corresponds to just Newton's equations of motion. So the two requirements are that your average path variable undergoes purely classical dynamics and that the difference between the forward and the backward paths goes to 0. And in that limit, classical limit semiclassics emerges. So we think we've solved our prefactor problem in this sort of different way by simply eliminating it. But we're still working on the numerics of this method because you can see, of course, that our quantum limit is now doing exact quantum mechanics. And so we now have all the challenges involved in finding all of the paths that go between point A and point B and identifying the ones that contribute the most. And so we have various strategies to do that. But I just wanted to end with this sort of summary of the exact path integral for a correlation function basically requires two independent sets of forward and backward paths to get a correlation function. If you do a stationary phase, that gives you what we've been calling quantum limit semiclassics. If you do a stronger than stationary phase approximation, where you allow only classical paths to contribute and you require that the forward and backward paths coincide, you end up with classical limit semiclassics. And of course, our MQC effectively takes you from quantum limit to classical limit semiclassics. And what we're calling the Filonov filtered path integral is actually taking you this way to the classical limit with all of the same degrees of freedom as one would like. You still can mix the extent to which you quantize these different degrees of freedom, and that's what we're currently working on. Okay, so I've tried to tell you about this nice method we have for a rigorous mixed quantum classical implementation, and there are, of course, some bottlenecks, but we think we have a good understanding of how these paths in phase space work and how to control the oscillatory structure of the integrand. I'll also just point out that we do host a GitHub page where we keep all of this code available to anyone who wants to do semi-classics, so you don't have to write your own double Herman clip from scratch. And with that, I'll just thank everyone in the group who's been involved in this. Shreyas is currently working on the Filonov filtered path integral. This is our Zoom group shot from now over a year ago. And these are all the people whose work I've been talking about for a while. And Greg Ezra, who's 2 doors down from me, is an excellent collaborator on this topic. And thank you all for your attention.